Hi, my name is Shreya, and this is my Physics 2211 Lab 5 on the falling motion of a slinky. So the purpose of this lab is to determine the motion of the bottom of a falling slinky as it falls through the air. So some models we can use for this lab are Newton's second law, which tells us that the net interaction between a system and its surroundings is related to its observed momentum. And then I use the velocity update formula and the position update formula to help track the position and velocity of the bottom of the slinky. And I also use these in glows. So another important force we should consider here is the drag force. Drag force is going to point opposite to the direction of the slinky's motion. And then it's important to note here that magnitude is proportional to the square of the speed. So as the velocity and the speed of the slinky changes, the magnitude of the drag force will also change. So to give a preview of the results, the bottom of the slinky does remain stationary in the air until the force of gravity outweighs the tension force. And that was kind of one of the key findings of this lab. So here is the initial conditions. So in this case, the system is the slinky, and the surroundings include gravity, the tension/compression force acting upwards, and then the drag force, which would act opposite to the motion of the slinky. And since the slinky is falling down, drag would act upwards. So, and then I also included the mass of the slinky. In this case, they didn't tell us the mass of the slinky in the video, so I just left it at 0.1. And then I added the initial position and velocity vectors, which I found using GlowScript. And the initial velocity, since it's released from rest, is just 0. And then the time step, which is 0.033, got that from tracker. And then B, which is a proportionality constant for the drag force, is also something included here. It is pretty small, and I think that's because I left the mass of the slinky to be so small. So here's some experimental details. So first I used the tracker to analyze the motion of the slinky as it fell through the air. And then I generated the GlowScript model to create a theoretical model versus the true motion of the slinky. And then I graphed the results in Excel. So here's a video of the tracker analysis. And as you can see, the slinky is just kind of, the bottom of the slinky is kind of staying constant until there's like a point here where gravity overcomes like that tension and compression force and it falls down to the ground. So I use tracker here to just kind of obviously track the motion of the slinky. And then I use GlowScript. And because there's kind of like two different sections where it's stationary, the bottom is stationary, and then it's moving, I actually separated my GlowScript analysis into two sections. So in the first section, the tension force is equal to the force of gravity because the slinky is stationary. Um, and then I used the velocity update and position update formulas to track the movement of the um, bottom of the slinky, and then obviously changed the time delta using delta t, and that was up until 6.433 seconds. And then in a second chunk, I went to the end of the tracker analysis, which is 8.067 seconds. And here, we no longer have that tension force acting upwards, but instead we have the drag force, which is going to act, which is going to oppose the motion of the ball, of the object. And so that is kind of the other force that's acting on the slinky here. So here's the results. I think the observed and expected motion is a little bit different from what we expected. And that could just be because the B, which is proportionality constant, is probably too high, based on the trial and error analysis I used. But it's important to note here that the observed and expected positions are constant up until that slinky finishes compressing, which is in alignment with what we expected to happen. And so, in conclusion, the bottom of the slinky remains stationary until the forces of gravity overcome the tension force, and some sources of error could be errors in estimation with the drag force coefficient E, inaccuracies in tracker placement, and then the fact that we didn't actually know the true mass of the slinky. So I created a what if question here, which just says, what if the slinky was longer? And if the slinky was longer, it would have taken longer for that tension force to be overcome, and the bottom of the slinky would have spent more time stationary in the air. And that's it.